Artificial intelligence began with something that has no intelligence at all, a switch. Imagine enlarging an AI chip until it covers an entire city. Now imagine walking inside it, searching for the place where intelligence lives. You might expect to find a tiny brain, a chamber filled with memories, or perhaps something hidden deep inside the machine, silently thinking. But all you would find are electrical pathways and billions of microscopic devices called transistors. Inside a digital circuit, these transistors control electrical states. Engineers represent one range of voltage as 0 and another as 1. A single transistor does not understand language. It has never seen an image. It cannot remember a face. It does not know what a question is. It does not even know that it exists. Yet when billions of transistors are arranged into carefully designed circuits, they can perform enormous numbers of calculations. Those calculations can process images, generate language, recognize patterns, and run the artificial intelligence systems we use today. The AI speaking to us now is physically powered by countless changes in electrical state. 0 and 1. Signal and no signal. One tiny operation followed by another. And this raises a strange question. Did humans truly invent this principle? Or did we discover a pattern that nature had already been using for billions of years? To explore that question, we have to go back to the beginning of human life. Every human body begins as a single cell. That cell divides into 2. 2 become 4. 4 become 8. The process continues until one cell has become trillions. As those cells multiply, they begin to specialize. Some become bone, some become blood, some become muscle, some become eyes capable of detecting light, and some become a brain capable of asking questions about its own existence. The first cell does not contain a mental picture of the finished human body. It has no mind. It has no imagination. It does not know that it is building a person. It follows genetic information, responds to chemical signals, interacts with its environment, and changes according to the biological processes of development. As vast numbers of cells communicate and respond to one another, the form of a living body gradually appears. No single cell builds the entire body alone. The body emerges from the relationships between all of them. Deep inside those cells, we find DNA. The genetic information in DNA is written using 4 chemical bases, A, C, G, and T. None of these 4 chemical letters knows what an eye is. None of them understands the shape of a bird's wing. None of them has ever seen a tree, a whale, or a human being. But when these bases are placed in particular sequences, read by cellular machinery, regulated, and combined with signals from the developing organism and its environment, they help guide the creation of living things, from microscopic organisms invisible to the human eye, to trees that live for thousands of years, from whales moving through the ocean, to the human brain that eventually learned how to build a computer. The brain itself reveals a similar pattern. A single neuron does not contain a childhood memory. It does not know love. It does not understand fear. It has no private knowledge of sadness. A neuron receives signals from other cells. It processes those signals through electrical and chemical activity. When the conditions are right, it sends a signal onward. The human brain is estimated to contain tens of billions of neurons. One widely cited estimate places the number at approximately 86 billion. Those neurons communicate through an extraordinary number of connections. Some connections become stronger through experience. Others become weaker. Some networks respond to images. Others participate in movement, sound, language, emotion, and memory. From the coordinated activity of these networks, our thoughts and experiences appear. The evidence does not point to one neuron or one tiny location that contains our entire identity. What we call the mind depends on patterns of activity spread across a living network. Scientists use the word emergence to describe this general kind of phenomenon. Emergence occurs when many limited components interact, and the complete system displays properties that no individual component possesses on its own. We can see this in an ant colony. A single ant does not know the complete design of the nest. It does not carry a master map. It does not command the entire colony. It responds to scent trails, obstacles, temperature, food, and the behavior of nearby ants. When thousands of ants follow these local rules together, the colony can find food, organize pathways, divide labor, defend itself, and construct a complex nest. The colony can solve problems that no single ant can solve alone. We see another example in a flock of birds. Each bird maintains its distance from nearby birds. It adjusts its speed. It follows the local direction of the group, and it avoids collisions. From these few behaviors, thousands of birds can turn almost simultaneously. The flock twists and flows through the sky as if it were one enormous living creature. No bird inside the flock can see the complete form. The form emerges from their movement together. Language offers another way to understand the pattern. A single letter carries very little meaning. Letters become words, words become sentences, sentences become stories, and a story can make someone laugh, cry, question a belief, or change the direction of a life. The entire story is not hidden inside one letter. Its meaning emerges from sequence, context, and the relationships between all its parts. Music works in a similar way. The number of basic notes is limited, yet rhythm, pitch, timing, silence, repetition, and harmony allow us to create an almost unlimited variety of music. A single note does not know sorrow, but a sequence of notes can bring back the memory of someone we lost many years ago. Now look deeper, beyond the brain, beyond the cell, beyond DNA. At the physical foundation of everything around us. The neurons in the human brain and the transistors inside a computer chip are both made from atoms. An atom contains a tiny nucleus surrounded by electrons, described through quantum mechanics as distributions of probability. The nucleus occupies an extremely small fraction of the atom's total volume, while containing almost all of its mass. This is why people often say that atoms are almost entirely empty space. That statement is useful as a comparison of scale, although the surrounding region is not simply an empty box. It contains electron distributions, electromagnetic fields, and quantum behavior that cannot be represented accurately as tiny solid balls orbiting through nothingness. The desk that feels solid beneath your hand, the ground supporting the weight of your body, and the hand of another person touching your own, are all composed of atoms structured in this way. When you place your hand on a table, the atoms in your hand do not pass through the atoms in the table. Electromagnetic interactions between electrons, together with quantum rules such as the Pauli exclusion principle, prevent ordinary matter from collapsing through itself. The sensation we call touch is created by interactions between atoms. The solid world we experience emerges from invisible forces and quantum rules. Matter feels continuous to us, even though its structure at the atomic scale is profoundly different from anything our senses directly perceive. Enormous amounts of energy can also emerge from processes occurring at this tiny scale. Einstein's equation, E equals mc squared, describes the relationship between mass and energy. Because the speed of light squared is an enormous number, a small difference in mass can correspond to a tremendous amount of energy. In nuclear fission, a neutron can strike the nucleus of certain atoms and cause it to split. That event releases energy and additional neutrons. Some of those neutrons may strike other nuclei and produce further fission events. The number of reactions can continue to grow, creating a chain reaction. We can imagine it in simplified form. One event leads to two. Two lead to four. Four lead to 8. The real process does not double perfectly at every step. Some neutrons escape. Some are absorbed without causing another fission event. The exact behavior depends on the material, geometry, neutron energy, and many other conditions. Inside a nuclear reactor, the chain reaction is carefully controlled. The released heat can be used to produce steam, turn turbines, and generate electricity for entire cities. The sun produces energy through a different nuclear process. Deep inside its core, extreme pressure and a temperature of roughly 15 million degrees Celsius allow light atomic nuclei to fuse. Hydrogen is gradually converted into helium through a sequence of nuclear reactions. The final products have slightly less mass than the particles that entered the process. That difference appears as energy. Energy generated in the sun's core slowly moves outward. Eventually, some of it travels across space and reaches Earth. It warms the planet. It drives much of our climate. It allows plants to grow. And it supports nearly every form of life we know. Fission and fusion are different processes. Yet both reveal how interactions at a scale far smaller than we can see can produce consequences large enough to power a city or illuminate a planet. This pattern appears repeatedly across nature. One cell divides and eventually becomes a body. Individual ants follow local signals and create a colony. Birds adjust to their neighbors and create a moving formation. Neurons exchange signals and participate in thought. Atoms interact and create solid matter. Nuclei react and release enormous amounts of energy. Simple components can produce complex results when they interact within the right structure. Artificial intelligence follows a related pattern. Inside neural network systems, including large language models, many mathematical operations are connected across multiple layers. Numbers enter the system. They are transformed according to learned parameters called weights. The results move forward and influence later calculations. One operation does not understand the world. It does not know what a cat is. It has never stood inside a house. It has never looked at the stars. And it has never wondered about the meaning of life. During training, the system processes enormous amounts of data. Its internal weights are adjusted repeatedly so that its outputs better reflect patterns found in that data. One adjustment means almost nothing. After a vast number of adjustments, the network can capture complicated relationships. It can learn patterns between words, structures within sentences, regularities inside images, relationships between concepts, and sequences that commonly follow one another. These mathematical processes are executed by electronic hardware built from billions of transistors. The transistor does not understand the image it helps generate. It does not know whether a sentence is true, false, beautiful, or frightening. A single mathematical operation does not understand the answer that eventually appears on the screen. The capability of the complete system arises from architecture, connections, mathematics, data, training, and computation working together. This leads us to a much larger question. If complex abilities can emerge from simple interacting units, must intelligence begin with something that is already intelligent? The brain is built from cells that do not think on their own. The human body develops from a single initial cell. A colony is formed by animals that cannot see the complete system. Language grows from a limited set of symbols. Music grows from notes and silence. Solid matter arises from atoms, fields, forces, and quantum rules. The energy of stars comes from reactions between nuclei far too small for us to see. And modern AI emerges from vast numbers of calculations carried out on hardware whose smallest switches recognize only electrical states. Perhaps humans did not create the underlying idea of artificial intelligence from nothing. We observed the brain, we studied neurons, we learned how simple units can exchange information. We discovered that networks can develop patterns that are difficult to find in any individual component. Then we reconstructed part of that broad idea using silicon, electricity, data, and mathematics. An artificial neural network does not reproduce the human brain in every detail. The two systems have very different structures. They learn in different ways. They consume energy differently. They have different strengths, limitations, and histories. The resemblance exists at a general level. In both cases, large-scale capabilities depend on interactions among many smaller components. This does not prove that AI is conscious. The ability to generate an answer does not demonstrate the presence of an inner experience. Fluent language does not tell us whether a machine feels the meaning of its own words. We do not even fully understand how human consciousness arises. We know that the brain contains neurons. We know that they exchange electrical and chemical signals. We know that damage to particular brain regions can alter memory, perception, emotion, personality, and behavior. Yet we still cannot completely explain why physical activity inside the brain is accompanied by subjective experience. Why does one wavelength of light become the experience of red? Why can a sound awaken a memory? Why does the activity of a biological network produce the feeling, "I am here"? We do not have a complete answer. We only know that when many components interact under particular conditions, new system-level properties can appear. Humans often describe the world through pairs of states: dark and light, stillness and motion, birth and death, signal and silence. The natural world contains far more detail and continuity than these pairs suggest. But separating reality into measurable states allows us to observe it, describe it, and build systems we can control. We turned electrical states into 0 and 1. We turned 0 and 1 into instructions. We turned instructions into calculations. We turned calculations into models. And we combined immense numbers of calculations into machines that can now speak with us. Perhaps the roots of artificial intelligence extend much deeper than the history of computers. Perhaps they reflect a broad pattern that appears throughout nature. Small units can connect, connections can create patterns, patterns can preserve and transform information. Information can influence behavior. Repeated behavior can form a system, and a system can display capabilities that none of its individual components possesses alone. A machine that begins with simple electrical states can eventually produce an answer that appears to come from thought. Today, we do not know how far this process will go. We do not know what new abilities may emerge. We do not know whether complexity alone could ever produce consciousness. And we may not yet possess a reliable way to detect subjective experience inside a system fundamentally different from ourselves. What we do know is that the intelligence appearing before us is supported by components that possess no intelligence of their own, like a brain beginning with cells, like a body beginning with one cell, like a story beginning with letters, like music beginning with notes and silence, and like a universe that formed stars, planets, oceans, life, and human minds from a small set of physical laws. So did humanity truly create artificial intelligence? Or did the universe leave clues for building intelligence everywhere? Inside atoms, inside cells, inside colonies, inside brains, inside language, inside music, and inside every system in which small things connect and become something greater than themselves. Perhaps humanity did not invent this pattern. Perhaps we finally noticed it. We understood a small part of it. And then we learned how to build it again, using a different material. From cells, a brain. From atoms, a world. From transistors, artificial intelligence. And from artificial intelligence, what comes next? I don't know. Maybe.